Okay, let's move into 4.3 applied systems of equations. So this is going to look very similar to 4.1. The biggest difference is now we're going to have word problems up front. And then once we set up the word problems, then we're going to go through and solve them using the strategies we learned. So this one kind of involves that slope equation, y is equal to mx plus b. This is kind of a nice example because they give us essentially the equations that we'll need. America's consumption of corn has decreased at a rate of y is equal to negative 2.05x plus 120 pounds per year per capita since 1995. So it seems like a lot of things are going on with that sentence, which there is, but really what you need to take from it is this equation is going to model America's consumption of corn. And very similarly, asparagus consumption has decreased at a rate of negative 0.5x plus 105 per year per capita since 1995. In what year will the consumption rates be equal? So this is actually kind of misleading to say that this is a system of equations problem, because the strategy here is that I already have y, or my consumption, by itself on both equations. So I suppose technically it's a substitution system of equations, but really what you're going to do is once you set them up like this and you've identified that the y's are by themselves, well, you just set the two equations equal to each other. And this is a strategy you see a lot even with basic graphing. If you're able to isolate y and you have two separate graphs, we'll figure out where the two graphs touch each other. So then from here, we just solve for x using basic problem solving practices. I add 0.5x to both sides. I subtract 120 over. I divide both sides by negative 1.55, and then x is equal to 9.68. Now, the only thing we have to do now, approximately, is we have to kind of go back to the question and say, what does that x tell us? And that's one of the big goals of this section, is to translate, then solve, and then in the context of the problem, give an answer that makes sense. And so both of these were happening since 1995. So in what year will the two consumptions be equal? They will be equal to each other when, and so yeah, it says 9.68, and you might be thinking, okay, well, I'm gonna round up to 10 years, so it's gonna overlap in 2005, which is very close to being right, but it's asking in what year will they overlap, and so it's 9.68 years after 1995. And so it's about halfway through 2004. And so if something happens in 2004, we don't usually say, oh, 3/4 of the way through. We just say, oh, it happened in 2004. That being said, if you did all this work and did 2005 on your exam, I would probably still give you full credit, maybe take off half a point. Okay, this one is a little bit more difficult up front. But the problem solving process will be pretty nice, and there won't actually be a lot of thought going into what the answer means because it's just a straight math question. So here we're just translating equations. We want to find the two numbers that meet the following conditions. The first number is 5 less than the second number. 3 times the first number is 4 more than twice the second number. So that can be kind of dizzying if you just read through it straight, but instead kind of look at it sentence by sentence. So, I mean, the second sentence says the first number is 5 less than the second number. So to write that as an equation, I'll first establish our variables. X is going to be our first number, Y is going to be our second number. The first number is 5 less than the second number, so you take the first number, you take the second number, subtract 5 from that, and you should get your first number. So that is a little bit dizzying. The only issue that I see in that type of equation is which side to put the minus on. And that always helps me to kind of just throw in random numbers to check and see if it makes sense. So I don't really know what my final answer is, but let's just guess that my y is 10. So if my y is 10, I want that number, or my first number, to be 5 less than that. And that equation does just that. 10 minus 5 would get me 5. So cool. That's a great way to kind of check to make sure that if you have a simple subtraction problem, just check it out and see if it makes sense logically. The second sentence or third sentence says 3 times the first number is 4 more than twice the second number. Well, we see the answer in the bottom left, but let's talk through it. One of the key words in that sentence, there's several, but what I kind of key in on is that oof, that is a word that stands for equality. So I know that everything before that is going to be on one side of my equation, and everything after that is going to be on the other side. So now I see 3 times the first number, x is my first number, 3 times x is, I have my equal sign, 4 more than twice the second number, 2 times my second number, more means addition, so plus 4. So that's where that second equation comes. So it's that breaking that into pieces that makes it so this question with confusing and dizzying words going on becomes much more manageable to kind of set up those equations. And now that I have them set up, I noticed my x is already by itself, so it seems like it's a good case for doing substitution, and that's exactly what I did. So I plug in my y minus 5 into my x of my second equation, distribute it out to get 3y minus 15. I guess I repeat it. And then I subtract the 2y over. I add the 15 over. I find y is equal to 19. Now it's a system of equations, so I got to solve for my x as well. I plug in my 19 into my first equation. Subtract 5 from 19, I get x is equal to 14. And now what I could do is I could look back at my equation and try and figure out what it means in the context of the problem. But it's numbers. So I found numbers. That's my first number is 14. My second number is 19. That's honestly about as clear as I can get. And I would probably just take what I've written right there and box that. I think that's what I write. Yeah. So I'm fine with that. If you want to be super, super careful, that's what you would say. My first number is 14. My second number is 19. And this is also a really good question to check your answer on. It's not that hard to go through and say, okay, well, my first number is 5 less than my second number, check, and then maybe could write it out or just plug it into your equation to find that it also meets the second equation. Now, we're going to start getting a little bit more involved because we're getting into kind of those famous or infamous, probably more accurate type of questions where we have a rate and a time. So you may have heard of the whole, oh, a train leaves this station going that speed and another one leaves the other one, and it's almost, that's where I kind of hear who a lot of people who hate math say they lost it, is when this stuff comes up. It's really not that hard if you're able to kind of see a distance rate equation, and then if you're able to set up these systems of equations. So next time, I don't know how many conversations you guys have, but I always have these conversations. Next time it comes up, if someone's complaining about the train problems or the cars or the plane, be like, it's actually not that hard. Just I can solve them. Just set up the things correctly and you run from there. Okay. All of that was kind of a unnecessary aside. 2 cars leave Chicago at the same time, one traveling east and one traveling west. So it doesn't really matter the directions. What's important to picture here is that one's going in one direction and the other one is going in the opposite direction. After 5 hours, they are 495 miles apart. If one car is 3 miles per hour faster than the other, how fast is each car traveling? So this is one where I kind of like to draw a picture to get things all lined up. So I mentioned we have kind of a starting point that might be this vertical dash here. I have one car going east, one car going west. Like I said, it doesn't really matter as long as you're aware that they are going in opposite directions. And that is going to be, eventually we're going to find out their total distance is that 495 apart. Now we have to describe their speeds. So let's establish our variables, and that's key in any word problem. If I haven't mentioned it before, I really should have. Whenever you're doing a word problem, establish your variables so that you can kind of go back and trace back your steps at the end and give a regular person answer as opposed to a math person answer. So I'm going to say X is my car 1 speed. I'm going to say Y is my car 2 speed. And now I'm going to write my equations. So I know that after 5 hours, they are 495 miles apart. So I see that kind of distance formula at the very top of the slide. It doesn't really matter what speed they're going yet. We're going to break down that equation. But I know that the speed of 1 plus the speed of the other times my total rate is going to be equal to my distance. So my rate is 5, or my time is 5 hours. My rate is going to be the rate of the first car plus the rate of the second car, because they're going in opposite directions. And so if I do that times the rate, then I should get my distance of 495. So that's one of my equations that I just set up. And now my other equation comes from that last sentence. If one car is traveling 3 miles per hour faster than the other, how fast is each car traveling? Okay, well, let's say my first car is my faster car. So my first car, X, is going to be equal to 3 more miles per hour than my second car. So that's 3 plus Y. And that's our two equations. We have our two equations. We're going to, I mean, we could use elimination, but this also seems like a pretty nice problem for substitution because I have my X. So I have my X, I'm going to plug it into my first equation, and then I'm just going to go through and solve. So 3 plus Y gets me 3 plus 2Y. You can either divide the 5 by both sides, or I chose to distribute. Subtract, 5 times 3 is 15, 5 times 2y is 10y. I subtract my 15y over to get 480 is equal to 10y. And so my y is equal to 48 miles per hour. Now to figure out how fast my x is going, I plug in 48 and I see that my x is going 51 miles per hour. And so again, this is pretty loose. That is a correct answer. I'd give full credit. If you wanted to be extra careful and give a normal person answer, you could say one of my cars, or my slower car, is traveling 48 miles per hour and my faster car is traveling 51 miles per hour. Moving into mixing solutions. And this one is a type of a problem that seems super, super, super difficult the first time you see it. So if you need to pause the lecture a couple times on this question, I imagine a lot of people will have to do that. It's hard, but it's very procedural. And so once you go through the procedure 2 or 3 times, you sense a pattern and you say, okay, that's really only going to do like 2 or 3 things. And once I fill out everything properly, it's actually not that terrible of a problem. So we need 80 liters of a 60% solution. We have a 40% solution and a 90% solution. How many liters of each should I use? So it seems like we might not have enough information, but we're going to establish our variables. Let's say X is the amount of our 90%, Y is the amount of our 40%, because we want to find the different amounts of solutions. And now we're going to fill out a table, and this is the table that you're going to be filling out anytime you see these mixing solutions equations. So the first column is always just going to be a name. It can be basic. Sometimes people say the initial plus the additive equals the final solution or something like that. Whatever helps you keep things straight. You could do X, Y, then final. I just really name the percentages. That's honestly the least important part of your table, other than, again, it's to trace back what you're actually finding in the end. So those are my names. The next one I want to write in my table is the amounts of each solution. So I don't know how much 90%, I don't know how much 40%. I do know my final result is going to be, oh, it's actually a 60% solution, that's fine. It's a 60% solution, so ignore the name. So I know that I have 80 liters of that 60% solution. And now I'm going to go through and fill out my second chart, which is my percentages. Cool. Well, I'm just going to take each percentage and change it into a decimal. So 90% as a decimal is 0.9, move the decimal over twice. 40% as a decimal is 0.4, move the decimal over twice. And 60% as a percentage is 0.6%. So again, that's the percentage. Ignore that parentheses, the parentheses is wrong. So those are all of my percentages. So nothing that we've done so far is really hard. All we've taken is information from the question and put it into a table. And that's the process every time, at least in this course, we are dealing with these mixing solutions. And then the last column honestly isn't that much more difficult. We have to do multiplication, but it's the multiplication of the second two, or the amount and the percentages, so the previous two columns. So 0.9 times X, 0.4 times Y, 0.6 times 80. And so all of that table was kind of to set up the very last column, because that last column is how we're going to set up one of our equations, and then our other equation is going to be our second column. So that should make a little bit of sense. The second column is the amount. So I don't know how much x, I don't know how much y, but I do know if I add those two together, I will get the result of 80. So that's one of mine. And then the other one that I'm going to add up and set equal to each other is the last column. So that is 0.9x plus 0.4y is equal to, and then 0.6 times 80 gets me 48. And so all of that confusion and chemistry and everything flying around boiled down to a fairly simple table to fill out. And then once you filled it out, you get your two equations. And now we're back to just basic system of equation solving. So I believe here I actually switched things up and went with elimination. I chose elimination instead. And so I did elimination by taking my first equation and saying, I want to get rid of my x. So I have 0.9x plus 0.4y equals 48. Now I'm going to take my other equation, x plus y is equal to 80, and I'm going to multiply all of it by negative 0.9. So that's that concept that we saw last lecture is, okay, I would multiply the top equation by, well, 1, so it's not going to change anything. And then I multiply the bottom equation by the coefficient of x with a sign flipped, so 0.9 times, or 0.9, negative 0.9. And then I multiply the whole equation. So x becomes negative 0.9x, y becomes negative 0.9y, and 80 becomes negative 0.9, or sorry, 80 times negative 0.9 becomes 72. Now I add my two equations. I get negative 0.5y is equal to negative 24. Divide both sides by negative 0.5. Y is equal to 48. And then going back to the question for units, liters, 48 liters. And I had to find my x. I'm going to use my first equation, x plus y is equal to 80. Subtract over 48, and I find that x is equal to 32 liters. If you got a little bit lost in that elimination step because that was tricky and pretty fast, I would honestly probably do substitution in this case. I feel like substitution is easier for a lot of people. It's very procedural. In this case, you could solve for x and y, x or y, and plug it in. I just figured we've done substitution for every other example in this section, so why not give elimination its day in the spotlight? And that's it. You, again, if you want to be super, super, super careful, you would say, okay, I would mix 32 liters of the 90% solution and 48 liters of the 40% solution to get 80 liters of the 60% solution. That's too much. I do expect you to have units, so what I wrote down is kind of the bare minimum. But if you want to go above and beyond, you could say something like that.